Hi everyone, this is Nitin Sharma, partner at Antler India, and welcome to the next episode of Theory of Next. We started this series a few months back to build our thesis out in public, to actually be one of the few VC firms that share our thinking and get feedback from the audience and founders working in interesting spaces. And we covered EVs, DAOs, mental health, to a tremendous reception. And as we were talking about all these spaces, it struck us that we should talk about space next. So today we're bringing out our sci-fi nerds and our space nerds to talk about this very, very interesting topic. You know, space is not just about space technology because it underlies so many other things, ranging from city planning or military needs to crop insurance and weather forecasting. So it's actually a really, really fundamental layer. And of course, the awesome thing is that India has been at the forefront of this, whether you talk about the legends of ISRO, doing things with a bullock cart that NASA could not do, or sending our various missions for 1/100th of the cost, or down to Team Indus trying to send something to the moon. So this is what we're going to dive into. And no better person to do this than Rahul. Rahul Seth he had scouting for Antler India, but above all, he is an expert when it comes to space, and he's truly fascinated by this topic. So I'm really looking forward to this conversation. And Rahul's also been an investor prior to Antler in companies like Pixxel. And in fact, Awais, who is a really interesting entrepreneur who founded Pixxel, will be with us at the end of this episode. So let's get started. Welcome, Rahul.
Hi, Nitin. Glad to be here. Excited for the launch.
So Rahul, let's start with this thing you've been annoying us with for many months, that this is the geo moment of India's space tech. Now that's a big statement. That's a huge superlative given the impact something like that has had. So why is this such a big moment?
So Nitin, I agree with you. We've been talking about space for the last 70 years. We've been talking about the promise of space for everybody for the last 20 years. And in some ways it feels like maybe it's not materialized. But what's important to see is what's happened over the last decade. And that's been the phenomenal magic that's happened. So I'll come back to Geo and why I keep using that analogy. So Geo did three things when it did. The first is it built a very strong, fast, cheap network, which was the infrastructure layer on top of which everything could be built. The second thing it did was make very cheap devices to be able to access that network. One without the other is useless. And then they built applications on top of it. The same parallel, if you look at the space technology industry, the infrastructure layer is launch. Until you can send a satellite upstairs. Now the launch costs for that have dramatically fallen to the extent that it's become 1/200th when it started with the space shuttle launch back in '81. So that's one. The second thing that's led to this amazing magic happening is hardware miniaturization, partly driven by the smartphone industry as well. And that has led to smaller circuits which are available. That's led to better solar cells that are available. That's led to better battery technology, better transponders and communication devices that are available. So both of these coming together, and this is just the last 10 years.
It's just converged together.
They've all converged together. So if you want to call it the convergence theory of all of these things coming together literally over the last decade. And we'll dive deeper into it as well. But these two big things are what are now going to lead to the applications that are going to be built on top of it. So when I told you about the geo analogy, the network is the launch providers. The cheap devices is the small sat, CubeSat movement that's now taken place. And the applications are what's going to be built, and which is what I'm very, very excited about. Before we jump into it, we need to do a short primer on a little bit of the physics involved with this. So a primer on how to think about space, right? And I'll quote the great Douglas Adams for this, where he says, the knack of flying is to find a way to throw yourself at the ground and miss it. So what happens when you talk about sending something to space or sending something up? You basically, this something is what we end up calling a satellite. You put it on top of a rocket, literally like a Diwali pataka, but it's much better, much bigger, much better designed. We can go into the details of that. And it burns just enough fuel for just enough time without exploding to take it up there. Now, the moment it takes it up there, it gives it a shove on a side. And what this object, the satellite then ends up doing is it misses hitting the ground.
Yep.
And it goes into what we call an orbit. Now, what's critical for us to understand is there are three kinds of orbits that we generally end up talking about. The one that was most used is the geosynchronous orbit or the geostationary orbit. This is at an altitude of 36,000 kilometers. and it mirrors the Earth's rotation. So the satellite stays at the same point around the Earth. You can have it around the polar orbits, etc. A lot of different places.
That's what the PSLV, etc. were about.
Exactly. Launching very big satellites up there as such, initially for telecommunications and television, which still constitutes a very large part of the economy.
For the longest time, this is how we did SpaceTech.
Everything.
Why is that? Why did it have to be so high up?
So one, we needed to be above certain areas constantly. So we needed it to sync with Earth's rotation. And at that altitude, you're able to sync with it without falling down, as well as having the velocity required for the mass that you had. So we had really huge satellites, the size of
I'm remembering
many
some
rooms.
Of my...
These are our GPS satellites, our military satellites, our television satellites, our sat phone satellites. They're really massive.
Right.
36,000 kilometers. This is what we use for remote sensing, disaster management, etc.
Because it was a big size, you also had a huge launch cost.
Exactly.
So and that was what the big sort of holy grail for SpaceTech was to bring that down.
Exactly. And this is where stuff gets interesting, because we get to the other orbit, which is called LEO, low Earth orbit. So this spans anywhere between 200 to 2,000 kilometers. And now what can you do fundamentally? You put something on a rocket, you fire it, hope it doesn't explode, put it into orbit. And now you effectively have a camera in the sky.
Right.
Now that camera and that satellite can do three things. It can look towards Earth, it can look into the universe, it can look around itself.
That's really interesting. So it can look, so look down on the Earth.
Yes.
Look away, which is for space observation and telescopes, and look around.
Yes.
Which is for things like space debris, etc.
Yes. The first set that we sent up looked down at Earth. This is called Earth observation and imaging. This is what we use for disaster management, etc. All of this, as well as for telecommunications.
So the fact that there is you can now make these smaller satellites more useful by putting them in LEO, but you can do a constellation of them.
Exactly.
And then that is where sort of mass applications are
That's where possible. The magic is happening. Now this constellation, where it becomes interesting, it's closer, it's cheaper to launch, it's smaller, and with a bunch of them, you can literally have real-time coverage of the planet. So
interesting.
If you want to do like health diagnostics, think about it as you had the finger pricking insulin monitors that would be able to do it once a day. These small satellites are like a continuous blood glucose monitor. Yeah. Continuously able
and
to
that's
give
sort
you
of, so it's basically those two things coming together. You have the likes of SpaceX creating lower launch costs, and you have the miniaturization, etc., which is creating this geo kind of network, as you call it.
Yes.
Interesting.
And that intelligence and what you're able to build on that infrastructure is what is where we are headed over the next
application side of it.
Yes.
Yeah. So that was awesome, Rahul. The next question that comes to my mind is, what is the business part of and from our perspective, what is the venture opportunity? So as we move towards that, and you talk about this is a multi-trillion-dollar industry in a few years. I think it's about 400 billion right now.
Yeah.
So help us break down the landscape and what kind of companies do what.
Okay, super. Yeah, as you said, so the expected growth path is from a $400 billion today to anywhere from $1.5 trillion to 5 to 7 trillion as such, depending upon what report you choose to look at. But it's growing much faster is my personal belief. Now, when I look at the space technology industry, this 400 billion is broken into three segments. And I draw the analogy to oil for this. So you have upstream, midstream, and downstream.
Yeah.
Upstream is where the oil is extracted. Midstream is when it's transported. And downstream is where you refine it into plastics, petrochemicals, etc.
Petrochemicals, yeah.
Same with satellites and space in some ways. Upstream is satellite and rocket manufacturing. Anything that involves building the hardware required.
Midstream, and launching.
Yeah, and launching those rockets. And midstream is the communication between whatever you've launched upstairs, getting that data back. Yeah, so transponder systems, etc. And the last, which is downstream, is the most exciting bit where all these applications are being built on top of it to do everything. So this is where Planet Labs, Cropin, etc. come in as companies. With rockets, if you look at it, the biggest innovation in a lot of ways has been reusability of rockets.
Right.
If I break a rocket down, the two hardest things to solve for within a rocket are one, obviously the engine, so that it doesn't blow up, which is very, very common, even after you've perfected it. And it takes companies 10 to 15 years to get there in some ways as well.
Not for the faint-hearted,
The second part is obviously the communication, ensuring that it's able to follow the flight plan, come back on board, navigational computing, which is what is also utilized to land it back down. These are the two hardest problems to solve.
So are there startups in India working on these areas?
Yeah, absolutely. So in India, you have the likes of an Agnikul and Skyroot. Skyroot builds multi-purpose, multi-stage, large-scale and small-scale rockets as such.
Okay.
where Agnikul specifically focuses on 3D printed rockets. The second bit, in addition to launch providers who are making large rockets, small rockets, you also have people who do in-orbit transfer. So once you get to a certain orbit, if you want to move into a more fine-tuned orbit, a company in India that does this is Bellatrix.
Got it.
Globally, you have Orbital ATK, a lot of other folks who do this as well. So this is primarily the rocket bit. The satellite bit is manufacturing the satellite, manufacturing the specific payload, and then coordinating and creating satellite constellations to be able to do this. So you have the likes of a Planet Lab that does this globally, makes its own satellites. They also come back later into the picture. You have the likes of a Pixxel that does this in India as well and makes its own satellites to send up for particular use cases. So this is primarily what downstream constitutes.
Upstream.
Upstream, sorry.
Yeah. And then downstream is where you have applications and software-like attributes, software margins and exponential growth possible, right?
Yes, that's the really interesting bit. So once you have this, what can you do on top of that? And that's where the magic is happening. So you have what I would sort of call satellite or space adjacent companies that utilize this data for their core business, like a Cropin or an Aqua Connect that does it for farming and aquaculture farming. You have in some ways space native companies like SatSure that primarily focus on providing this data and analytics to companies who are going to use it, whether it's BFSI, whether it's agri-tech, etc. You have full stack companies that operate satellites and sell the data and sell the analytics on top of that data to different players. So this is someone of the likes of a Pixxel or a Hypersat abroad as well. Then you have, outside of just these applications, you have people who are using this for orbital debris tracking. $250 billion. Out of the $400 billion, $250 billion is downstream. About $108 billion is upstream, and about $30 to $40 billion is midstream.
Got it.
So this is where the opportunity lies.
Interesting. So now we want to bring it back to this whole geothesis. And the first part of that was launch costs.
Yeah.
So let's start quantify this a bit.
Sure. So if you look at launch costs, they were originally close to $1 million per kg.
Okay.
The best ones that are useful for parallels are $85,000 per kg was the cost on the first shuttle that went up back in '81, which is about $300,000 in today's money. Now that price came down to $10,000 per kg with the first Falcon rockets in 2016, and it's expected to go sub $1,000 per kg.
So it's gone from
$300,000
to
40 years ago in '81 to close to $1,500 today.
per kg.
Per kg. And the expectation is over the next 10 years to 15 years, this is expected to go down to $100 per kg, close to like, well, not close to, but close to airline rates in some ways.
Yeah, I mean, it's sort of following a price curve that you see in technology.
Exponentially decreasing price curve. So that's one of the biggest things. And again, it's been driven by two things. One, reusability.
Yeah.
Second, multiple smaller rockets being available. And private sector coming into building a lot of this, because this was originally just the domain of
government.
Yeah, nation
So
states.
the second thing you talked about was hardware miniaturization.
Yeah.
So how do we break that down?
Now, literally because of smartphones, the camera technology that we have has gone up exponentially, from the sensors that are used, to the lenses that are manufactured, to the number of precision lenses that can be manufactured at scale. So the costs have dramatically fallen for it as well as the size has become smaller. Now, the moment the payload is smaller, the battery you need to run it is smaller, which has also gotten better. So now what's happened is, at the same time, the solar cells that you need to do it have gotten smaller. The microprocessor you needed on satellite to be able to do stuff has shrunk in size as well.
So everything is smaller.
Yeah.
You can pack it more compactly, and the price per kg to send it up has become much lower.
Smaller as well.
So you have a combination of these, and what this means is that it makes the smaller satellites that were in lower Earth orbits far more effective.
Yes,
far more powerful.
Far more useful. And now at the price of one large satellite, you can deploy like 20 small satellites and about a constellation
of 20 CubeSats.
CubeSats, and that's also the standardization framework that's sort of helped, which has allowed for component standardization across industries. It's still not gotten to the level of auto parts manufacturing, but it's headed there.
Yeah.
So what this now does is, with the cost of one satellite, which would only cover one region, you can send up close to 20 to 30 satellites to have a constellation that covers the entire globe 24/7.
Wow.
And what you can do is amazing on top
And
of
then, because you have that sort of substrate, you can do a lot more in applications.
Absolutely.
So that's what we are calling the geothesis.
So these are the two macro trends that are being driven globally as well as in India. The interesting bit, and this is where the geothesis gets more interesting, is what's happening in, why is this particularly for India.
Yeah,
and what's happening
so let's connect it to two other things, right? Which is this is all good, but you need the ecosystem, you need talent, and you need government support, right? So let's talk about, are there just more people now who are working in this?
Yes, very interestingly, ISRO set up this college in 2007 called IIST. There are about 40 colleges in India that offer degrees in aeronautical engineering.
Wow.
IIST was specifically set up to produce space technology graduates, and they were a direct pipeline to ISRO, where they had a contract at ISRO. So the first batch graduated in 2011, wrapped up their contracts by 2016. They have a batch size of about 200 people. So you now have 200 people who have close to 10 years of experience in this industry who are now coming out to build stuff. They've seen this being built at ISRO every year from 2016 onwards, and they're all now adding up. So that's one thing that's happened. The other thing that's happened is the first generation of space companies that were built in India, say Earth to Orbit, Team Indus, Devas to a certain extent as well, created a talent pool that's now building second generation things. The third, and this is where with the convergence of technology, talent, and this is where government support gets very interesting. If you look at the US as a parallel, SpaceX exists because there were NASA grants available for them to exist in so many ways, given just the costs associated with everything. ISRO today provides testing facilities, access to know-how, technology transfer. A lot of ISRO scientists have been very generous in sharing their experience, their time, their know-how with individuals, young individuals who are coming out and building this. So you have the ISRO talent pipeline, you have new folks who are coming into it, and the support that's given monetarily as well as from the technology perspective. That's making it super booming in India.
Interesting. Okay, Rahul, so now that this geothesis is clear, we've mapped out the landscapes. So if we have to pick 3 or 4 things that are most interesting from your perspective for startups in India, or opportunities that we think people should pursue, I'd like to go into that.
Super. So just to start off with, the biggest opportunity from India, this is where I will preface, there are opportunities globally, but what is something that we can do given the constraints of the ecosystem that we work with is what we'll focus on. So while hardware is what captures the largest amount of attention, we'll spend a lot more time, particularly on the software side and the application side, which is where we see more venture value in so many ways.
That's just for this, just to be clear, just for this episode, we've chosen to focus on the application software.
Application software, yeah. So the most important is what I call space adjacent industries, which are using all of this data and all of this technology that's now available to apply it to real life problems that they're solving. A prime example of that is Cropin, which focuses on agriculture, but they focus a lot on utilizing satellite data to inform farmers of crop yields, pestilence, ground composition, etc. Another example of this is Aqua Connect, which focuses on aquaculture and helping farmers do it. And this is where space adjacent is very interesting, is when you're able to monitor this, a large number of these people are underserved with credit. So the aquaculture farmers, this allows large insurance companies as well as credit providers to be able to look at yield, to be able to look at potential future.
So these things have been talked about for a long time. I think what you're saying is because of the as you call the geo moment, the LEO, all the data. So you have these satellites being more effective, and it's not just sending imagery data. It's actually that you can now use this in more interesting ways around credit scoring and all of that, insurance, etc.
Yes, and because the costs of all of this have gone down, it's easier for a lot more people to do it. So hedge funds and large insurance agencies already bought this kind of data for their work. Now you have NABARD buying this data.
Data is just, that's the end result of the geothesis. Data is so cheap. Space data is cheaper now.
Far richer in quality, so not just 3G, 4G. And now you can do amazing things.
So this is space adjacent companies.
Yeah. And then you also have space native industries in this, like say SatSure, which are focused on aggregating the data, finding analytics, and providing it to different companies in this space. Companies like SatSure, companies like Pixxel, they're building their own platforms out for people to be able to sort of literally plug and play and find out what's happening. This actually brings me to the second interesting opportunity. So far, buying this kind of Earth imagery data or Earth observation data is a very broken experience. It's still done over emails. Sometimes you literally maybe print it out and then go by hand on top of it, like, okay, this comes out, that comes out. So these companies which are now building platforms are streamlining the process of acquiring this data, and then you being able to analyze it on their platform itself. So this is where the transition from services to product is happening more as well. So these are two opportunities which are there about how do you utilize different kinds of data to be able to do actual real world things. And in addition to that, which is also an opportunity area, is to own the satellites. Now that's more capital intensive, but then you have stronger moats because you own the imagery that you're going to build stuff on top of. The second area where I'm particularly excited about is space infrastructure being built out. So this is relatively easier than rocket engines in some ways, but this involves orbital debris tracking, fueling stations, communications in space itself. So all of these are areas that are growing and maturing, and nobody has a head start in this area. Everybody is starting to get into it as well. So we're sort of on a level playing field across the world. Capital requirements are also significantly lower because you're not building rockets again,
so
which is the most
space
expensive
adjacent startups, space native companies, but still essentially being on the application side. And the third is in space
work that you're doing.
Yeah.
Yes. And the third is what you do with a satellite and how do you make that satellite better. One big part of a satellite energy expenditure is to be able to beam the data back down. So being able to do onboard processing, edge computing as we call it, it's an actual good use case of edge computing in so many ways, because if you're able to analyze it, you're only able to send insights down rather than having to send massive data sets down.
So Rahul, this has been a really fun discussion, and I know one of the things we've been talking about is in some of these episodes bringing someone in who's actually an operator, a founder in the space doing something very interesting. So we've talked about so many really cool things towards the end with asteroid mining and in space manufacturing. So I think we should have our friend Awais join us.
Absolutely.
Awais, as many of you know, is the founder of Pixxel, a company that the whole ecosystem is very proud of, and so we're really excited to have him here.
Hi folks, we're back with Awais here today. Awais and I met 4 years ago, and it's been an incredible journey. He's the founder and CEO of Pixxel. They've built the company from ground up through multiple stages to having their first hyperspectral satellite being launched very, very recently. The images are back on ground as well. They're looking very sharp. We have Awais here to discuss some crazy stuff with us. We've talked about all the realistic things, the economy, how does the science work, what makes sense. This last bit is the fun bit where we want to talk about the crazy stuff that we hear, the science fiction that we hear, and how close is it to being a fact for us today. So Nitin, I know you've asked me a lot of these questions. I haven't been able to answer them as well, which is why we have Awais here today.
I mean, I think it's a great time to talk about some more out there stuff. I think we've talked enough about some very practical things, but the real joy of space is the dream, right? The way it sparks imagination. So maybe a good point to start is just everybody keeps hearing of Elon Musk amongst the 100 things he does. Talks a lot about the ultimate mission is to make humans in multi-planetary species. So, Awais, is that something which is really important?
Yeah, I would say it's not only important to become multi-planetary, but multi-stellar eventually, taking a step beyond what Elon says in terms of becoming multi-planetary. That's just step one, and then we need to become multi-stellar. There are two reasons I would say for that, right? One is the fact that it de-risks us as a civilization, as a species. Humans are unique as far as we know in terms of the intelligence that we are able to show, which means that it becomes a important thing for us to actually not have all our eggs in one basket, so as to say. There are events such as an asteroid hurling towards the Earth that we might not be able to deflect. There are things such as super volcanic eruptions that can happen here that might lead to Earth becoming inhospitable for a few centuries, which is why it becomes important to have a second home where we can actually be de-risked from planetary extinction events. And then there are also entire solar system based extinction events where it might be a gamma ray burst that happens somewhere in the vicinity of our galaxy that makes all of the planets right in the pathway of not being habitable, or a rogue star can come hurling around towards our solar system, uprooting the gravity wells that are here, right? So I think there's those logical reasons, but then I think the more important reason is that we humans have always had an exploratory zeal. We didn't, if there was something that wasn't attainable, humans sort of went out and said, let's see what's out there. When humanity started in the cradle of Africa, the humans didn't say, we have enough resources here. They expanded towards Asia. From Asia, they expanded towards the Americas. From Asia, they expanded towards Indonesia, and they didn't stop there. They said, let's see what's beyond these seas. So it must have been some crazy people who built out some initial rafts and said, let's go out to an island and started civilizations there, right? So I think just because of that exploratory zeal, we have sort of covered the entire planet. Now it becomes important for us to see what's really out there beyond the Earth also. So that's, I think, the second and probably the more important reason for us to become multiplanetary and multistellar.
You know what? Why this is awesome, because it's really fun to talk about spaces, no pun intended, where you're not thinking about what's a series A, B, C, because for something like this, we're talking about completely different level of ambition, right? So, but what about time frames? Like, what do you guys think? Like, is this something which we can achieve in the next 50 years, 100 years?
Yeah, I think it depends, right, on the incentives that are aligned. If we wanted to do it with the current technology that we have and with the current resources that we have, it's probably a 10-year job for us to actually create a thriving Mars ecosystem. And we could have probably done that by the turn of this century if we had continued on the same level of pace that the Apollo program went on. In about 6 years from when Kennedy announced it, when they had no technology to do it, they landed people on the moon. And that was because the entire nation and the people said, this is something that is important, has to be done. And then it wasn't important anymore for the senators that were taking calls. So, it was pulled back. So I think it's a call on incentives there as to how we can make it happen. But it's not a question of if it'll happen, but when. But whether that is 20 years or 50 years remains to be seen. But I think from the pace that is picking up, and not only from government, but from private organizations like SpaceX and Blue Origin, I think realistically, probably in 20 to 30 years, we'll have some sort of a basic base on both the moon and Mars eventually. But as to whether it's a thriving economy will remain to be seen as to how different factors come together.
And what is the beyond sort of ambition and focus, right? And when you say the entire computing capacity of, I think, the Apollo mission is today on a phone, or I've seen that kind of stat thrown around. Yeah. So do we already have everything we need in terms of the science to get there and the engineering to get there, and it's really a matter of just pouring more resources, or are there important bottlenecks which will take a few years to get sorted?
I think there's obviously a few small engineering challenges that have to be solved to get there. We haven't done all of it at the scale that is required, but the delta that exists between where we are today to having a thriving Mars or moon base and the delta that the United States had when it had to send people to the moon in 1962, that delta was much, much larger than it is today. There will always be new problems to figure out. We still don't know what the impact of radiation will be on the people that will be traveling long distances in space and being there. But that's something that will only come out once there's actual data to take it. So I would say, yes, we have all the scientific and engineering related knowledge up to a certain point needed to get there. It's just a matter of the funding and the will of the people to get there.
Wow, just have to make myself live long enough to see this. What else do you personally find fascinating?
I've always found the idea of asteroid mining very interesting. Right. We've talked about it, and I think this is one of the things we should talk a little more about.
Yeah.
Why are we mining it? Like our general belief is just mine resources, we'll use it to make something. That's the fundamental idea. But why asteroids? We have a lot of it here.
Yeah.
And that's the interesting bit in so many ways for me. So, Awais, you mentioned we're looking to be a multiplanetary species right now, then multistellar. So where does asteroid mining fit into the picture? Is it that critical a piece of it? Is that why we talk so much about it?
Yeah, I would think, look, asteroid mining has been talked about in the sense of bringing riches back to Earth. There is an asteroid full of gold or diamonds and platinum, and we'll bring it back and we'll be rich. That doesn't really make sense. Probably the first one or two folks that do get asteroids that are valuable can create a monopoly like the De Beers have done with diamonds in South Africa, for example. But what you actually need asteroid mining for is to have resources for you in space, not to be able to bring it back to some planet. There's a big chunk of space literally between Earth and Moon and Earth and Mars and between different galaxies. And to be able to get from here to there and create an economy that sort of links all of these bodies together, it's important to also have infrastructure in space that does it, whether that's large-scale manufacturing facilities in space for habitats or research facilities, right? Some things can be uniquely created in space, such as pharmaceutical drugs can be researched. You can create high-purity Z-band optical cables that can only be done in space. To be able to get material from the surface of the Earth to space is actually a lot expensive because of the gravity that Earth has. But when you're looking at creating large-scale structures in space that might, either power lunar colonies or Earth colonies or Mars colonies, and you need large antennas to be be able to communicate over far distances. You need much larger interstellar ships eventually. Where will the material come from? You do not want to take it from the Earth. The Earth should be designated as sort of like a national park where you're maintaining the sanctity and the ecology that's
Our
there.
species is roaming around. Yeah.
You
our
get
endangered species is just roaming around.
So you need material in space for space to actually create habitats in space. And it's not only that when humans expand outward, they're going to go to other planetary bodies. They're actually going to be in space creating our own.
So the entire new sort of space economy, right? We don't, all the things we talked about is sort of the terrestrial way to look at
It's
the
all
space.
here.
This is actual space economy where things are being manufactured in space, used in space, transported in space.
Absolutely.
And the reasons I think Awais you started talking about, it's just physics and costs and gravity. Yeah. You don't actually need, you cannot envision a world where these things are payloads. They have to be literally mined and manufactured in space. So how far out is this?
I would say, we have already reached asteroids thanks to NASA and JAXA. The Japanese Space Agency and the American Space Agency. We have reached asteroids, we have collected samples from there, and we are bringing them back and have brought some back as well. The engineering challenges to actually mine and process minerals is still something that needs to be tested out, so we are not completely there. But if I were to give a time frame, 15 years is optimistic to be able to actually mine something there, and 25 to 30 years where this becomes a fully fledged economy.
When do you think we'll have the first space factory, whatever that means? And what will it look like?
So it depends. So space factory for Earth or space factory for space. So for space factory for Earth, Wada Space is already sort of doing it where they are doing small scale experimentation and manufacturing, which they're going to bring back to Earth, such as optical cables or pharmaceutical drug testing.
So do you actually, I know you mentioned that I've read the arguments for it, but does this ever make sense? I mean, what's an example where a drug, you would think that it would actually be cheaper to manufacture
it's
a
not
drug?
So much as cheaper as
possible.
What can you detect in space? You don't have gravity in space, you have microgravity, so that removes a lot of constraints in terms of your protein building and whatnot, which gives you a lot more space to play with. So that's the laboratory you can only build in microgravity. We don't have anti-gravity machines to do that here on Earth, so it has to be done in space. So that's why it sort of makes sense there. The other thing again is when you're trying to create organs for humans, 3D printed bio-organs, gravity creates a lot of problem because you're building very thin layers of tissues that need to be around each other and they don't need to collapse on each other. So you need microgravity. Again, you can't create microgravity.
So for you, in space manufacturing sounds like the most interesting things that will happen in the Earth orbit is drugs and organs.
Yeah, in the short term, right? You need to create a lower Earth economy first. For you to create a space economy, it's in the lower Earth orbit. We have a robust economy on Earth. At a certain point in time, Europe, Asia, and Americas were quite disjointed, but today it's like one single world.
Right.
So to expand outwards, we need to first create a low Earth economy, which is space manufacturing for Earth and in space economy right there itself in terms of fueling and whatnot. Then you expand towards the Earth and the Moon economy, for which you'll need this infrastructure, and then you move towards Mars, which will be linked again to the Moon and Earth. So that's sort of like the natural progression of how things will probably come to be. The lower Earth economy is the MVP for solar system economy.
Yeah, it's the MVP of the test bed. Yeah. What does India? Where does India factor in Awais in all of this? Like, what are we going to sort of be closer to? I know you're doing something very interesting, but when you see the landscape and the number of new people coming out of the institutes, are they still largely focusing on things that we discussed earlier, Rahul and I, or are there enough people thinking about these things?
So I think there's been a difference in how the Indian Space Agency is set up and versus ESA or NASA has been set up, right? ISRO was set up to bring domestic Atmanirbharta or self-reliance to our country. They had to create technologies that were already created and catch up and leapfrog in certain areas to provide infrastructure to the country so that we are not dependent on someone else, versus a NASA whose job was pure research and working on cutting edge research and doing things for the first time, similarly with JAXA, right? So that's sort of been there because it was a necessity for ISRO to do that when it started out, versus some other space agencies like we just talked about. But where we are today with the privatization of the economy is in-space has been spun off. So all the commercial related activities can now be taken up by in-space, leaving ISRO free to do the job that space agencies are supposed to do, which is work on cutting edge research, such as sending solar probes to the sun or sending interplanetary probes to some far-off planets. So since that is opened up now, I think it's more of a level playing field between countries to say who can actually go out to the new strategic playing field, which is space now, and assert its geopolitical will.
So multi-planetary species in space manufacturing, asteroid mining, space debris. I've learned a lot. So thank you, Awais, for joining us. I know this was a short segment. We would love to continue this conversation. Rahul, thank you for all your insights. I think this was one of the more sort of out there episodes of Theory of Next. So thank you all for joining, and we'll see you next time.